Hello, my name is Sebastian Rickelhoff and I would like to welcome you to my talk Semimartingales with Killing and their Force Characteristic here at the German Probability and Statistic Days. In this talk I would like to introduce a concept of killing similar to the Markovian concept, but in a semi-martingale framework. Moreover, we want to consider the characteristics of such a semi-martingale with killing. This leads to various problems which do not occur in the classical theory. During this talk, we mostly follow the notations of Jacot and Sheaif's limit theorems for stochastic processes. But more important, we consider a new state space, which we will call E tilde, and which is the original state space, namely the Rd, together with two different points, infinity and delta, where infinity and delta does not belong to the Rd. These 2 points will later play the role of killing points. We need 2 killing points, unlike the Markovian theory, for example, where we only need 1 killing point, because we will consider 2 different possible ways a process is able to leave the original state space Rd. Of course, we need some calculation rules for these 2 points, but I don't want to state them here. Only the 2 most important are stated, for example, that the norm of infinity and delta equals infinity. Moreover, we want to consider a stochastic process in continuous time and with values in E tilde on a stochastic basis where the filtration and the sigma field are both generated by the process. Next, we are going to define 2 stopping times. The first stopping time is a sequence of stopping times actually and is called sigma n and is defined at the first time t when the norm of xt or the norm of xt minus is greater or equal than n for all naturals n. The second stopping time, zeta partial, is defined as the first time the process xt leaves the original state space Rd, or in other words takes values in infinity delta. And with the help of these 2 stopping times, we are now able to describe the 2 possible ways the process x is able to leave the state space. And we are doing this with 2 other stopping times. The first of these stopping times is called c to infinity and is defined as it is stated here. And we think of it as an explosion killing. If we consider an example pass, we clearly see that the process explodes out of the original state space towards infinity. This stopping time is rather easy to handle because it is predictable. Harder to handle is the second stopping time we want to define and which we will call c to delta. This stopping time is defined the other way around and we think of it as a sudden killing. If we again consider an example pass, we clearly see that the process jumps at time c to delta out of the original state space and towards delta. Such a jump possesses height infinity, which makes it so hard to handle for us in the later theory. Therefore, we mostly consider this kind of stopping time in the later theory. At this point, I want to mention that although these 2 stopping times seems quite artificial, this is not the case, because both can occur naturally, for example, as a solution of a stochastic differential equation or in the context of Levy processes. Moreover, with the help of these 2 stopping times, we are now able to define a proper concept of a process with killing. To this end, we define a stochastic process x with values in E tilde as process with killing if it takes values in the original state space, the Rd, between 0 and the minimum of the stopping time c to infinity and c to delta. Between the minimum and c to delta only take the value infinity, and after c to delta only takes the value delta. And again, I've drawn an example pass where the minimum of the 2 stopping times is c to infinity, and one clearly sees that a transition from infinity to delta is possible, but not from delta to infinity, or from the set infinity delta back into the Rd. So it is obvious that the both points, infinity and delta, are the killing points for the process with killing. And with the help of this concept, we are now able to define semi-martingales with killing. This kind of processes will be called generalized semi-martingales in the following, and we call a process X with killing and the well-known killing times c to infinity and c to delta a generalized semi-martingale if the stopped, or more precisely the pre-stopped process x alpha n minus is a semi-martingale for all n in the naturals and all stopping times alpha n, where alpha n is defined as a minimum of the sudden killing c to delta, and tau n, where tau n is an announcing sequence of the predictable stopping time c to infinity. This means that it is a sequence of stopping times which converges to c to infinity from below. In this definition, we choose the stopping time sequence alpha n to make sure that the pre-stop process is always a classical semi-martingale, and to make sure that we are able to define the classical characteristics for this stopped or pre-stop process. And exactly this is what we will do in the following definition. We consider a generalized semi-martingale with the associated classical semi-martingale and the characteristics Bn, Cn and νn. Then we call the processes B and C and the random measure nu the characteristics of the generalized semi-martingale X if they coincide with the classical characteristics of the classical semi-martingale X alpha n minus on the stochastic interval 0 alpha n. The natural question which arises now is, are we able to characterize a generalized semi-martingale with the help of the three characteristics we just defined? The answer to this question is no, because the random measure nu, which compensates the height of the jumps of the process, is not able to compensate a jump of heights infinity. But a jump of heights infinity occurs at time c to delta, and at the jump to delta itself. So we are in the need of a new characteristic. And we will call this characteristic the force characteristic of a semi-martingale. This concept was introduced by Alexander Schnur in 2020, and we call the predictable compensator of the stated indicator process the force characteristic of the generalized semi-martingale X. And by the definition we clearly see that it is the idea not to compensate the heights of the jump, which is, I mentioned it before, infinity, but to compensate the time it occurs. And with the help of this force characteristic of a generalized semi-martingale, we were able to characterize a generalized semi-martingale. And exactly that is stated in the following theorem we are seeing here, but I don't want to comment on it any further because it is a bit longish and it is close to a theorem of the classical theory of semi-martingales, which one can find in Jacot and Cheryaev. Moreover, I've marked the parts orange which differ from the original theorem. With this in mind, that we are able to generalize the theory of semi-martingales with the help of killing and the theory of characteristics with the help of a new characteristic, I want to end this talk. Moreover, I want to thank you all for your attention.